So here's your trapping zone definition. Accessible location on or within the equipment. Accessible, a hazardous situation is always accessible. Where a human body or part of a human body is exposed. So accessible means exposed to a trapping, crushing, shearing, impact, cutting, entanglement, drawing in, stabbing, or abrasion. So any kind of a casualty type injury caused by a machine hitting you is trying to be captured here, yeah? All right. And if you think about, stability falling on people, um, ultimately it's a trapping zone hazard as well. If you think about a falling mass because of a breakage of a support part, again, it's almost a trapping zone hazard. So you'll see the word trapping zone used in the 9.2 movement kind of thing. But gee, it belongs almost anywhere, The harm is almost from the trapping zone hazardous situation. So the mechanical requirements are always a hidden, the hidden secret there is that there are no safe limits. They're always language like, it's not going to be bad. Nobody's going to get hurt. This shall not happen. There shall not be an unacceptable risk. And so, so that's in some ways not very black and white. And so when judging mechanical hazards, in fact, you really benefit from people who have some experience and are aware of, the history of what's good and bad. And that's, I would second that as very true. There's not this, 100 microamps is bad, or 90 degrees C is bad, or 43 C on an applied part. We can't have something higher. These are the black and white things that standards are great at trying to give us. But with mechanical hazards, I'd have to say that sometimes we'll be disappointed if we're looking for that. There's too many variables is the reason. People would love to specify, once you're 22 kilograms, falling mass is dangerous. The problem is it's not always true. And so, maybe it's 12 kilograms, whatever it is. So you have, the body parts that have different hardnesses. Your skull's pretty hard. So it could be brittle maybe, and yet if you have softer tissue, there might be more forgiveness for a mass or a force. And is the shape of the object, is it shaped like a sword or is it shaped like a ball? How fast is it? What's the mass? The momentum or the inertia. So there's a lot of variables, and I guess that's the difficulty. I guess from a risk management point of view, and that's the bottom line, is these are being judged almost from a risk management point of view. If you remember with risk management, we kind of think about, with electrical and thermal, often we can say, well, it's kind of death. If worst case scenarios, we're looking at death here. We're looking at shocks or fire. And so we need pretty low probability, right? But with mechanical, sometimes we're talking about somebody's finger or discomfort, which is less than injuring a finger. And so would we allow that to be a little more frequent? Well, I don't think we'd want to admit that too explicitly, but there's implicitly, in fact, we do. That is what the historical and the expert people who can judge these things, in fact, that is what happens. And so again, it's hard to specify a limit because it depends on the severity of harm that we expect. All right. So if you look in 62.368, which is a standard that's been rewritten to take into account um, hazard-based safety, I think they call it. In other words, like 601 third edition with risk management results, they've in fact tried to specify numbers, and I'm not going to show you those numbers, but they do, and they're in there. And so by all means, borrow them if they're applicable to you. In the medical standard, I hope you're going to laugh, but I'm being serious. Sometimes we think about the body part that's going to be injured, and we want to simulate it with, if it's a finger, a pencil, or a carrot. If it's something larger, soft tissue, you can almost think about the produce department in your grocery store. How much force is going to hurt something like a fruit? We can do the test with the fruit instead of trying to hurt ourselves. And so how much force is going to be there? And so we can simulate our machine with some piece of produce and get a feel for when harm occurs. But remember, the standard's worried about as soon as there's discomfort, so it's not just injury. All right. Anyway, that, believe it or not, I want to mention that because I think it's helpful. I think it kind of gives us a feel. And so if you don't have a lot of experience, you start doing mean things to cucumbers and melons and pencils and carrots, you're going to get experience. You're going to start to find out real world what happens. All right. So motion's great if that's what we intend. We want things to move around. But we can also see that can be a hazard. And so gaps are a risk control. And gaps that are so narrow you can't get in there and never open enough that you can get in there are okay. Gaps that never close such that they would crush the body part that's most at risk are also okay. So we want to design gaps, ideally, that would satisfy either of those approaches. Another approach is to keep the trapping zone, the hazardous situation, away so that it can't be reached. That's a safe distance. And there's a machinery directive supportive standard that talks about, a gate around an industrial robot and whether you can touch a hazard. So there's some A, B, and C numbers, and 9223 does that. This gap of 9222, in fact, benefits from a machinery directive support standard as well, harmonized standard, if you will. And I'm going to show you that table in a minute. The third dot talks about guards and other risk controls. And so a guard is a mechanical guard, keep us away from the traffic zone. But you can think about electronic guards as well, a light curtain, a beam of light. As soon as you break the beam, the traffic zone goes away, et cetera, et cetera. And of course, that's single fault safe. And then the third is, well, okay, because of the intended use, we have to allow access, the possibility of access to this traffic zone. These other three approaches would be nice, but we need to allow the X-ray tube or whatever it is, the surgical robe, surgically, the robotic assisted surgical arm. We have to allow it to move, and the possibility that it could do trapping zone type harm needs to be something we live with. But we're going to rely on the operator to be trained and aware that injury won't occur. And so that's this continuous activation approach, where continuous activation is talking about a dead man switch. As soon as you let go, you have to hold the switch continuously to have motion. As soon as you let go, it stops. And that needs to be in a single fault safe way true. Or a single high integrity thing. But that can be tricky because how fast you move affects response times. Are you really, do you have a good visual field of view for the hazard? All those things would have to be true for that to be effective. All right, but if you took any one of those four, that's considered a suitable risk control. And here's, gaps are pretty popular. So this looks very black and white. If you're worried about a body, you need to be more than 500 millimeters, or if children are involved, also 500 millimeters, and no other, so you're never going to be closer than 500. You're always bigger. So with the head, though, it's sort of that max min idea. So if you're never closer than 300 or bigger than 120, if you're never bigger than 120, the head will never fit in there. And if you're never closer than 300, the head will never be crushed, even though you could fit in there. But you have to consider whether a child could be involved, a patient child, say, and then you'd want to keep that gap less than 60 so the head can't fit in there, et cetera, et cetera. The toe and the foot are very popular, 50 and 100 numbers. 120, oh, sorry, and 50. So, so it looks black and white, right? You're thinking, oh, wow, I love standards. But how do we know that we only have to worry about an arm or a leg or a head? Sometimes that is the gray area. And so we don't quite have the black and white. But with feet and toes, we kind of know. And then with fingers, we kind of know. So this is very valuable for fingers, toes. All right. So speed of movement, especially for that continuous activation, there's a separate 9226 clause, so I wanted to point it out. It talks about speed of motion, but there's another point here, and it's stopping distances. And so stopping distances is hiding in here. And you can see I added some square brackets, meaning text that isn't here, but maybe should be. And over travel. So the over travel, stopping distance of such movement occurring after operation of the control to stop the movement shall not result in a risk. Okay, so a very important concept, because in reality, that's what we've got to worry about. Okay, and so that is related to the continuous activation 9225. In fact, there's no distances, though. So it's a great example. Such that the movement occurring after operation shall not result in acceptable risk. See, this is you read that and you're like, yeah, okay, that's a good requirement. How do you know how to verify it? Okay? Because you have experience. The particular for 52 is that all X-ray? 52 is general X-ray, 44 is CT, 64. Is that invasive X-ray? Like angiogram? I don't know. I think so. Anyway, in 2-1, which is linear accelerators, you're going to find these numbers. Rotation, stopping distance, linear stopping distance. So you've got these 10 millimeter, 3 millimeter rules, 1 degree, half a degree, 3 degree. The standards talk about 2 speeds. You can go a normal speed when you're far from hitting, but once you get close to a hazard, to an arm situation, you need to slow down. And so those 2 situations are talked about here. Now, does every piece of, say, linear accelerators meet these requirements? I wish I could say yes. Sometimes risk management's used, and I'd have to say usability would be a better way to describe it. And distances slightly larger have been justified. Okay. And that sort of speaks to the whole problem of how to put those into a general standard if the particular can't even do it. All right, so if you're doing the continuous activation, you need two means to kind of implement that dead man, unless you somehow wanted to argue you had a high integrity kind of a switch, but with the low voltage kind of things, you wouldn't. So there's generally an enable drive or, cut power kind of thing. Cut power would cut power sometimes to the processors that are in the motor drive. So if we don't have to reboot, I suppose sometimes we try to implement things. So generally you have this push in and then push forward or backward, right and left for the movement, or squeeze it and then with whatever's the applicable drive, do your thing. And so you can still do it with one hand, but you're in effect engaging two switches. And if you let go of either one, it would stop. And the point is, you'd normally let go of both. And if one hadn't detected that, the other always would. And so in the particulars, that's specified. In the general, it just makes the comment that it needs to be single fault safe. So if we think about a PEMS, a programmable electrical medical system or subsystem, there's going to be a processor that talks to a servo motor controller. And the motor controller might even have a processor. And then this processor needs a watchdog, and that's a processor or, piece of clock hardware. And so things that are doing safety checks need two means to stop movement. So you would cut power, like to the servo controllers, motor controller, or you would have an enable line on the motor controller this is the operator. So the operator's got his own feedback vision, if you will, and he's doing his dead man switch, in which he can cut both of these or initiate a drive. So sometimes the drive itself can be a safety means to stop. If you think about putting a 0 on the motor controller, is that really safety reliable enough? Or will we do it the old-fashioned way? So that's a design decision with the burden going to the drive, whether it's safety or not, or we won't try to demonstrate that. We'll have these other two. So whatever you're doing, but generally this watchdog would want to be able to shut things off. The processor, just with normal feedback about sensors, would want to be able to shut it off. And so you're shutting off the power or the enable on the motor. Now, when you do that, do you need a brake as well? Well, that's something that's possible. And that brake would have to be a cut power, and the brake engages kind of a thing. And there might be a power line on the brake that you're controlling. Is there going to be redundant sensors about position? Yeah, probably. So a PEMS is a risk-driven development lifecycle approach on the hardware side. And then when we get into the software, this has software that we're writing. Does the motor controller have firmware? Sure, that's software. It might be the commercially available one, and you're kind of doing high-level things, or it might be your own. Microcontroller's yours. So in any case, a risk management driven development lifecycle approach for the software. So clause 14 talks about say the hardware side of it, but also the software. And then you have that 62304 standard, which explicitly talks about your software development. So this is common enough that I thought I'd better discuss it, at least within the motion control. But then we could be talking about temperature control here, whatever, hazard, radiation control for that matter, clinical function controls, central performance, if you will. Microprocessor controlled things are quite common now. All right, so you get the idea. All right, back to switches and things. So sometimes if dangerous things could happen and it's the go switch, you want to make sure you don't accidentally go. So you have to kind of shroud these things. See, if you hit that with the palm of your hand, it's not going to go. If you accidentally step on this, it's not going to go. So you want those kind of ergonomic design, usability kind of things. And in fact, it's required. Okay. And on the other hand, if you want it to stop, you don't want to shroud this thing. You want to be able to hit it with the palm of your hand. Okay. In a panic situation, you got to make it very easy. But now you're stopping, not going. And there's all sorts of requirements about two kind of motions. So if you slap it down, but to turn it off, you take it, twist it. So those are two different motions so there's some intention that you're, allowing motion to continue. It can't be confused with the intention of stopping. And, it has to be near any operator that would want to stop the motion. It has to be within a meter or whatever your usability would say. It has to be accessible. And, single fault safe and, switches that have been tested for 10,000 or ideally 100,000 cycles. Of course, they're starting to fall within that high integrity. If in fact they're rated for, say, stalled motor currents and things like this. But generally within control, low voltage control, we're looking at redundancy kind of things. At some point, this switch might be great, but then it's talking to a lot of other switches, right? All right. Yeah, that's that. Technically, the standard doesn't require an emergency stopping device. Equipment theoretically now today is pretty safe without an emergency stopping device. But I suppose we'd always realize that we need to provide one. It's not so much because the equipment's dangerous. And I suppose, we don't want to be too confident that it couldn't be, but it's single fault safe. I suppose those things are very useful still for operator problems, right? So sometimes the operator doesn't know what he's doing. And so somebody else can have a safety measure for an operator. At the very least, it's still useful for that. Can they prevent injury? Probably not. Can they prevent serious injury? Hopefully, yeah. So they have value. And do they make people feel good, right? If you were going to have surgery with a robotically assisted system, would you feel better if you saw an e-stop on there? Sure. But is it a false sense of security? Sure. Anyway, all right. Another important concept, release of patient. 925, nice new header. Traditionally, if you think about somebody high up on a table, you need to be able to lower that table even if there's no power. If somebody went into a gantry, we'd like to get them out of the gantry. And so that's certainly what we mean by release a patient. But in terms of robotically assisted equipment, surgical equipment or system, we need to realize that also means to be able to take the tools out of the patient So sometimes the machine's in the patient instead of the patient in the machine. So release of patient, we need to realize that in a general sense could be either of those situations. Okay.